It's about fuzzy dark matter.
Anyway, today I'm going to talk about fuzzy dark matter. It's the lightest dark matter nowadays. And then there's some issues between the Lyman-alpha forest measurement. And then I'm going to present this fuzzy dark matter in tension with the Lyman-alpha forest. This work is collaborated with Professor Chen, Chen here, and his master student, and really good, and the Professor Zhong from the Chinese University in Hong Kong, and he's a PhD student. Okay, story always starts from if we want to hunt dark matter, what kind of things we can do. And then the famous story is look at this diagram. People look at the interactions between the dark matter and the standard model particle interactions. And then one can measure the missing energy by creating the dark matter in the collider, or one can try to measure the recoil energies by taking some heavy target underground, try to measure this recoil energy. Or recently getting more and more hot, if you heard this damn story, if there is some unique features, yeah, from the thing we know about standard astrophysics spectrum, astrophysics background, that could be some dark matter. And the last one is just we discussed if dark matter and the dark matter has some interactions. Then this kind of interactions might change our galaxy's structures. Then these things, it can provide us with another windows to look at these dark sectors. So dark matter is just expected to have weak interactions between the standard model sectors and the dark sectors. But it's not necessary. It's not necessary to be. Then, if there is no interactions or very, very weak interactions, what's the features? And then, if in that case, so-called collider, dark matter directed detection, indirect detection doesn't work. People need to look at the structures of our galaxies. So let's look at this famous diagram. In this diagram, it draws this dark matter rule, and then there's huge magnitudes in the dark matter mass and dark matter interactions as well. And then, in principle, I draw this line. It's roughly 100 TeV. If assumed thermal dark matter and the unitarity limit is true, then in some sense, in our life limit, yeah, we might able to these small characters. This means reach. It's not very confident, but yeah, in some sense, in our lifetime, we might be able to explore up to here. So I call this line is called reachable right edge. On the left hand side, people always talk too much about wind in this side. How about the left hand side? We need to think about, yeah, how about this light kind of dark matter things. This so-called astrophysics action. Actually, it's very well motivated. In QCD action, which you can solve these strong CP problems. And then if you look at this action spectrum, it's also large from the 10 to minus 13, 10 to 23 electron volt. And then in this mass, if you calculate its related density, then you can see below 10 to minus 30, it can behave like dark energy. And then when you put smaller than 10 to minus 25, related density is high enough then can contribute to dark matter. So if we are today talking about the actual dark matter, then the mass region it should be greater than 10 to minus 25 or 10 to minus 24. And then in these regions, most of the regions has been excluded by different, for example, Lyman-alpha forests and some supernovae issues, gravitational wave issues. But in this window, although it has some problem of a Lyman-alpha forest, but it's very attractive. It can solve the related density, it can get the collider related density. Also, it can solve this small scale crisis. Let me explain why it's a small scale crisis. Lambda Cold Dark Matter, a small scale crisis has three different things. First is the so-called missing satellite problems. These three problems is compared to the Lambda Cold Dark Matter simulations. And then compared to the measurement, so far, there is the cosmological problems and the too big to fail problems. What is this three? Let's have a look. This is figures between the dark matter halos densities profile. This is dark matter halo radius from the galaxy center. And then the pink line, which here use our simulation, which is NFW-like. On the other hand, our measurement, here I need to emphasize is around 10 to 7 solar mass to 10 to 9 solar mass. Those of the galaxies, satellite galaxies, they found in a small radius regions, the density is flatter. And then they also check this velocity rotation curve. And then, of course, the rotation curve here use how much matters inside. Then you can see, compared to data, this is a block data. And then this is a simulations. This lambda CDM simulation give you too much velocity or too much body and matters inside. And then on the other hand, for the missing satellite, the simulation tell you there's a lot of subhalos there. However, currently they measure just in the order of 30 or 40, order of 50. Compared to the order of several thousands, still much smaller in our Milky Way. So, if we want to save these three, one need to have a new mechanism to give the velocity, dark matter velocity as a kick, a boost. And then, there's several ways to solve these things. Of course, people can solve this one by using the standard model feedback, but nowadays, the standard model feedback, lots of the so-called heating and the feedback from the supernova things cannot explain all the mass spectrums. I mean the subhalos mass spectrums, satellite galaxy mass spectrums. So, those of astrophysics approach can certainly reduce, but it's hard to explain much all the observations over the full range of the halos. Just like how I told you, the problem is only appear between the 10 to 7 to 10 to 9 solar mass. But if one want to explain one thing, cannot explain three things. So, in this case, these problems just by solve astrophysically still remains an open question. So, let's see. Then, what is the Lyman-alpha forest? Lyman-alpha forest is a very cute idea. If you might see this kind of phenomenon all your life, you see the light from outside the windows, and then the light, when light hit the dust, you can see some dust around the inside the light. Similar idea, if you assume there is a flash light, like quasar, emit a lot of photons. And then the photons pass through lots of hydrogens. And then, of course, assuming hydrogen has the same distributions as a dark matter, then, or affected by dark matter, then when the light propagates through lots of hydrogen gas, they will observed by hydrogen atoms, and then, therefore, in the spectrum, light spectrum, you will see some peaks, some kink, and then absorbed by the hydrogen atoms. Then, because we know the redshift, we know where is the dip is, then we can clearly tell in our sky where is the dense regions, where is less dense, where is denser region, where is less dense regions. So by using this way, we can try to figure out that this is spectrum looks like. We can try to figure out what is the halo profile. Then people claim by using this technique, they can, in this March, they claim SQ100, they claim, okay, 10 to minus 21 should, fuzzy dark matter should greater than this one. And don't forget, at the beginning I say, if you have a mass heavier than 10 to minus 21, then this fuzzy dark matter cannot solve these small scale problems. So these small scale problems is very crucial in the least mass regions, 10 to minus 22. So this group claim is ruled out. And that group is almost in the same time, it's come from both. It's also claimed is ruled out again. However, in last year, Lyman et al. They claim currently lots of measurement is getting more and more precise. And on the other hand, in the past we used to ignore lots of feedback uncertainties, lots of standard supernova feedback we used to ignore. And then we used to use warm dark matter as a fuzzy dark matter simulations. Means we are not really doing the fuzzy dark matter. Then he given two problems before people want to claim 10 to minus 22 electron volt fuzzy dark matter has been ruled out. He claimed people need to watch out these two conditions. And then that's the motivations we want to do. So our goal is including the quantum pressure, which is important for the fuzzy dark matter in the simulation. Second, we want to present, based on this kind of simulations, what is our Lyman-alpha forest constraints on fuzzy dark matter. Okay, for the fuzzy dark matter, we assume it's a superfluid. So there is some similarities. For dark matter, it is no interactions. For superfluid, it's no viscosity. So it's similar things. So we can take the, but on the other hand, dark matter assumes a particle. There is a lot of small dark particles, small dots there. So it's a discretized stuff. But for superfluid, it's a continuous. It's described by I-wave functions. So there is the numerical challenge is how do we match or how do we go from this, use this technology to understand the particle dark matters. And then indeed, that kind of a small mass, 10 to minus 22 electron volts, it gives you the matter wavelength is around 1 kiloparsec. So the idea is very simple. Yeah, we just insert the gravitational potentials into the Schrödinger equations, and then do some algebra. We can have three equations. One is come from continuous equations everyone familiar with. Second from the energy momentum conserved equations. And then don't be careful. If you compare to the superfluid things, you can find we have additional terms. It's called quantum pressure. And then let's watch closer. This quantum pressure has one singularities. And then this singularities occurs at the density, dark matter density at 0. And then when this dark matter density at 0, this quantum pressure could get to the infinity. This is not simple or to solve numerically. So we try to do, and then we use the Gaussian kernels as a dark matter, as a fuzzy dark matter solid cone density profile. and then we solve these Schrödinger equations. In the end, we get the quantum pressure acceleration term. And then let me show you. For this quantum pressure, you can see in some regions it behaves like push the particle away. Some radius regions it looks like attractive, everything inside. And then if you look at the positions, the behavior in some regions, they will be confined in some small or radius regions, small regions. This behaves like boson-Einstein condensations. Let me show you the two-body simulations here. You can see the blue line is if we consider the two solitons with the Gaussian distribution density profile, they meet each other. And then if we are consider the quantum pressure, they just meet and then sum together and then pass through. However, if you consider the quantum pressure, you can see a lot of this. Yeah, a lot of these fluctuations. So, then we try to understand this quantum pressure from these two-body simulations. And then we found this is a direct solutions. And then this is a particle-particle methods which we calculate by using these Gaussian kernels. And then you can see if we give, maybe the color is a little bit light, but let me explain to you. If you doing the Fourier transformations in different frequency, then you can see our solutions about these particle-particle interactions match very well about n equal to 1 ground state solutions. And then these ground state solutions is the contributions of the lowest eigenstate of Schrödinger Poisson equations is largest than other eigenstate. So it's the most loudly the contributions in the density of heralds. So in these figures, we conclude our equations can be used as a very good approximations if we want to do the particle-particle interactions. Then, however, there's the other issues. If we try to solve this in the n-body simulations, sometimes we are looking for the density. But if you want to calculate the density, that is very time-consuming. Then we use some skill people similar to the latest QCD people does. We try to search do small simulations and then try to calculate if the density compared to the if we solve exact or use the approximations, what's the difference? Then you can see when the density much dense regions, there is some suppressions. Means you can see there is a cancellations if you do these interference terms. When they take this guy take a square, then if you use Gaussian and delta functions, they could behave different. Then we have taken into account these corrections, and then these corrections. Then we put these corrections into our simulations. If ideal case, let's look at ideal case. Means the initial conditions is not realistic. It's just from the rates. Then the red shaded regions is our numerical accuracy. Then you can see our fuzzy dark matter is kind of between. It's kind of lower than the cold dark matter. Lambda CDM simulations. So, which can help us to solve these cosmological problems. Then, next one, we try to do the cosmology simulations. Then we put really initial conditions from the fuzzy dark matter. Then fuzzy dark matter initial condition, it depends on what kind of fuzzy dark matter mass you are using. If you are using 10 to minus 21, then this is a Fourier transformation. This is wave numbers. This is a power spectrum ratios. It's co-transfer functions. It means the ratios between the cold dark matter and the fuzzy dark matter. And then you can see there is some separations in the small scale. Then we don't have time. Let me keep this one. Yeah. Compared to this is a lightest one, 10 to minus 21, 10 to minus 22, 10 to minus 23, 10 to minus 22, 10 to minus 21. The heaviest, the smaller separations at the small scale. Then we consider these 4 simulations. And then in these 4 simulations, we consider if we use only like observation people does, the 2 papers appear in the previous one, we just use the fuzzy dark matter as the initial conditions, and then or fuzzy dark matter with the initial conditions and the full simulation with the quantum pressure. And then same thing with the 10 to minus 23 as the conformations to check this guy is indeed is good or not. Then we found in a small scale, of course, the lightest one will give large separations. Then in a small scale, you can see a difference compared to the lambda CDM. Then let's see. Then we really do the data fitting. Let's take the data from the Lyman-alpha forest. And this is the layer data. Although it just gives a 3 redshift, we just focus on this redshift. So our data cannot be treated, our fit cannot be treated. It's relatively good, but it's not precise because we only use the 3 redshift. Actually, we should use a more redshift here. Then we can see if we use the if we consider whole spectrums, even 10 to minus 23 simulations can improve the chi-square than cold dark matter scenario. However, if you only consider the small scale regions, then 10 to minus 23 is strongly disfavored. However, it's hard to say the fuzzy dark matter with the 10 to minus 22 is disfavored. It's only 1.88 delta chi-square. And then there's the other issues. If we consider the Lyman-alpha forest clearly about their mass, and then as Langwei et al. Just mentioned, we should also take into account those of the temperature issues from the hydrogen gas. Then if we take the temperature uncertainties, this is a ratio compared to the cold dark matter. This is wave numbers. This is small scale. In a small scale, you can always find the same behavior if you change, if you play around the uncertainties of hydrogen temperatures, or you play with fuzzy dark matter temperature. I'm sorry, fuzzy dark matter mass. So they are almost parameter degenerate. So it's hard to say either the data is good fuzzy dark matter at the 10 to minus 22 electron volt, or is good the hydrogen temperature at some certain levels. So let me show you the conclusions. So we propose to use the Gaussian kernels to discretize the quantum pressures in order to use the particle-particle interactions for MRT simulations. We found it's still not yet to do out 10 to minus 22 electron volt by using the Lyman-alpha forest data unless the these hydrodynamic uncertainties are clear. So let me use this sentence as an end. Last, those of the problems too big to fail and missing satellites are addressed directly by fuzzy dark matter. But until we understand those of ionic physics and the feedback is more completed, we will not know whether the change in the property of dark matter subhalo implied by quasi dark matter is either required or useful. Okay, thank you.
Questions?
Okay.
I might lost at some point, but did you take into account the gravitational interaction?
Yes.
So usually we derive the quantum pressure from the Klein-Gordon equation.
Yes.
Then instead of Klein-Gordon equation, you have started with
self-gravitational layer, right?
Okay. So another question is the numerical. You have put delta function into the Gaussian function.
Yes.
So how can you check this scheme?
Yeah, we
This
check.
numerical scheme. Do you have any idea?
Yes, just this is very painful for check indeed. The first way, as I show you, let me show you some figures. If we just go to the, sorry, this is the, if we just see the two particle interactions, two body interactions, then you can see the blue line is a non-quantum pressure, and then the red line is a quantum pressure with a formula. The formula we calculate by using the Gaussian kernels. And then this block 9, we solve this quantum pressure booty force by solve the Schrödinger equations. Then you can see that when time goes, and then most of the time they agree each other only in the between. Sometimes the quantum pressure formula is needed a little bit, and then sometimes it's a little bit, but averagely you can see they can have a difference, but averagely I think they behave very well.
Okay, I see.
Thank you.
Okay, no offense, Sming Tsai again.